my name is Michaela Trujillo and I am from the New Mexico Institute of Mining and Technology. This summer I am at the University of Michigan conducting research under Professor Diane Bry and Dr. John Luntz in the Smart Materials and Structures Design Lab. In this video I will be discussing the geometric parameter study of the rib knit pattern actuation architecture. Active knits, like the one shown in my hand, is a actuation architecture that consists of continuous interlock loops of shape memory alloy. Shape memory alloy is a nickel titanium material that uses the shape memory effect to recover material strains and its original shape.
Shape memory alloy is a novel material for actuation because it uses the shape memory effect. The shape memory effect is when the material undergoes temperature and stress transformations. As shown in the diagram, a load is applied to a wire that is in the martensite twinned state. At this point, the wire undergoes a stress transformation and becomes deformed. When the wire is heated above its transformation temperature, which is about 70 degrees C, it recovers its original shape. At this point, the wire is in the austenite state. At the microscopic level, the crystal structure of the wire in the martensite twinned state looks similar to the one on the right. When a load is applied to the material, the atoms shift to the left. As the material is heated, the atoms rearrange themselves and form a rectangular structure. The motion between the atoms during these two phases causes the actuation motion of the material.
I am going to demonstrate the shape memory effect on a spring made out of SMA wire. In my hand I am holding a spring that is at its original shape. I'm going to apply a force to the spring, causing the spring to deform. As I heat up the spring, you will be able to observe the spring contract and return to its original shape. Here you have it. Active knits are a novel actuation architecture because it produces enhanced actuation displacements compared to a single SMA wire. The rib knit pattern is especially promising because it can be used as a surface actuator. However, the range of performance of this knit is still unknown. Therefore, the goals of this study is to first identify the geometric parameters that influence the kinematic performance. Second, experimentally determine the effects of these parameters on the performance. And lastly, examine the relationships of the parameters through non-dimensionalization.
The rib knit pattern is made up of two basic unit cells, the knit loop and the purl loop. As you can see in the figure, the ridges in the knit loop wrap around behind the legs, while in the purl loop, the ridges wrap in front of the legs. The rib knit pattern is created by alternating two knit loops and two purl loops to form symmetric columns. The rib knit pattern produces an accordion-like motion when heated above its transition temperature. To achieve our goals, 6 different prototypes were chosen and tested. A, B, and C had a wire diameter of 20 mil, and D, E, and F had a wire diameter of 15 mil. 3 different loop diameters to wire diameter ratios were chosen. A and D was more densely knit with a ratio of 11.81, where C and F had a larger ratio of 25.68 and were more loosely knitted.
This is the test setup we used to test all our prototypes. Here is the base plate. This is the stainless steel rod. This is the encoder reader that we used to take our measurements. This was just used to hold the encoder reader. We had our 2 Teflon bushings and our load. So to test our prototypes, the setup was in an environmental test chamber to heat it up and cool down the prototype. We placed the prototype under the base plate, making sure it was perfectly centered. We then applied a load to the prototype and heated up the test chamber to 120 degrees. At that point, we then took a measurement and then cooled it back down to 10 degrees Celsius and took another measurement. After we took the measurement, we increased the load and repeated that cycle.
During the experiment, the prototype heights in the austenite and martensite phases were measured. In this graph, these heights were plotted against the pressure. The actuation displacement is determined as the difference between the austenite and martensite heights. From the previous graph, we are able to plot the displacement versus pressure. This produces a unique actuation curve that displays a peak actuation displacement. The actuation displacement versus pressure curves of prototypes D, E, and F are all plotted on one graph so that the following trends can be observed. This plot was created using data from the previous graph. In this plot, the peak displacement and the pressure at the peak displacement are graphed against the ratio. We can see that the knits with a smaller knit loop diameter versus wire diameter ratio operate against higher loads compared to knits with a larger ratio. The more dense knits produce smaller displacements compared to knits that are less dense. Non-dimensionalization was used to examine the relationships between parameters in the prototypes C and F. In this graph, the displacement versus pressure curves for these prototypes were plotted. When the non-dimensional force was plotted against the non-dimensional displacement, the data was broken down and the peak displacements for both prototypes were around the same general area. This shows that the behavior at a given ratio is independent of the scale.
Now that you know a little bit about my research, I would like to share with you my experiences as an SROP student. This program has given me the opportunity to come to a world-renowned research institution and work with professors, research assistants, and graduate students. I've learned so much from the people I've worked with this summer and was able to get an idea for the type of research that was being conducted in the mechanical engineering department. I was also able to get a feel for what life would be like as a PhD student.